Hello everyone, this is Miss Yoon. In this video, I'm going to explain about the potential energy diagrams for exothermic and endothermic reaction as a review before we move on to another topic in this unit, because in the previous assignment, a lot of people wanted more practice problems. So first, we're going to look at the first diagram on the left. This chemical equation shows the decomposition of hydrogen peroxide into water and oxygen. As a reminder, anything on the left side of the arrowhead in this chemical equation of this arrowhead right here are considered as reactants. Anything on the right side of this arrow in the chemical equation are considered as the products. Now moving on to what these sections in the diagram represent. Number one represents actually the total amount of potential energy of the reactants only. In other words, all the stored energy in the bonds of hydrogen peroxide are represented in this section right here. So I'm gonna put potential energy of the reactant. Number 5 here represents the potential energy of the products only. First thing that you learned in this unit was collision theory. As a recap, in order for chemical reactions to occur, collision theory says that the reactants need to collide with the sufficient amount of energy at the correct orientation or angle. So the sufficient amount of energy that was required will be considered as the activation energy. And this energy is the extra energy that was added or basically needed in order for this reaction to begin and form the product as a result. So that extra amount of energy that was added from the potential energy of the reactant could be considered and represented using from here to here all the way to the top of the hill. Okay, so anything that was added here are considered to be the activation energy. Okay, so this number 3 is representing the activation energy, or I'm just gonna use the symbol of E sub A. So again, as a reminder, activation energy is just the minimum amount of energy that's required for this reaction to occur. Now, the activated complex is considered as a maximum energy point along this entire reaction path. In other words, it's just the highest peak in the energy diagram. So right here will be considered as activated complex from all the way bottom to the highest peak. So the activated complex is considered as the most unstable state. So on top here, it's very unstable. So what does that mean? I'm just gonna give you an analogy. So like imagine that we're all atoms trying to bond with another atom to produce a new product. And you spend more time and energy to meet that another atom. You're excited and happy at the same time at this moment, but also you feel very unstable at this point because you're not 100% sure if you're going to be happy with this atom at your final state. But once you decide to bond with this atom for good and like you feel like you've achieved your goals, you don't need to worry about anything, and like you don't need those extra energy that you already had or gained, okay, anymore, and those will be released to the surroundings. So now you feel very stable, and the total amount of energy at the end, which is here at the product, the amount of energy is now less from this activated complex. So activated complex is kind of like the intermediate state where things can actually happen for this reaction. All right, lastly, I'm gonna go over the change in enthalpy concept, or the delta H. So this is, again, as a reminder, delta H is equal to the potential energy of the product minus the potential energy of the reactant. So if I were to just give numerical values to the potential energy of the product and the potential energy reactant, as an example, I could just make this potential energy of the reactant as 5 kilojoules and the potential energy of the product as 2 kilojoules here. And in this case, if I were to just subtract those two numbers, the product was 2 and the reactant was 5. So that's going to give you -3. So this again meant that the delta H is a negative number. And when delta H is negative, that means that the energy is lost to the surrounding or released to the surroundings. And that means that this reaction is considered as an exothermic reaction. So why is this arrow number 4 right here considered as delta H? So I'm gonna highlight the potential energy of the product side only right now with this red right here. Okay, up to here is potential energy of the product. That minus the potential energy of the reactant, which is right up here. So if I subtract this entire thing, the green one, from this red here, is going to now give you whatever's left over from here to here. Okay, so that's why this entire section highlighted in yellow is considered as delta H. Now moving on to the second potential energy diagram on the right side. Now we're going to look at the reverse reaction of what we originally had. So in this case, the reactants are going to be the water and oxygen that are going to react together to form hydrogen peroxide as a product. So again, the potential energy of the reactants are represented here in number 1. Potential energy of the products are the ones that are in the at the end of the diagram. Okay, so that's interval number 4. No, actually number 5 in this case, sorry. The extra energy from the reactant that you actually added are considered as the activation energy, E sub A. The highest peak within this diagram is considered as the activated complex. And lastly, the delta H, or heat of reaction, that's another word for it, or the change in enthalpy is considered as here, this section, interval number 4. And again, if I were to give numerical value for the potential energy of reactant as 2 kilojoules in this case, and 5 kilojoules for the potential energy of the product, again, delta H is equal to potential energy of the product, which is in this case 5 kilojoules, minus the potential energy of the reactant, in this case is 2 kilojoules, and it's going to give you 3. So delta H in this case is positive number. You added the extra amount of energy from the reactant, which in this case was a lot, okay, compared to the exothermic reaction. So since this delta H is positive, we consider this as endothermic reaction. Notice that the potential energy of the product in this case is higher than the potential energy of the reactant, unlike the case in the exothermic reaction. So the product side is less stable compared to the reactant. Hopefully this kind of clarified more information for you, and now we're going to move on to some practice problems. Here is the first problem that we're going to be doing together. It gives you some extra information that we don't really need in order for us to answer the actual question. It says to state what interval 3 represents. And notice that these numbers here, the intervals, are not the same as the ones that we actually used in the previous examples. To answer this question, all you had to just say was that interval 3 is delta H, or change in enthalpy, or heat of reaction. So you can see that there are 3 names for this section number 3, only for this particular diagram. So another question could be asking you the same type of problem, but the interval number could be used with number 2 instead. Hopefully you understand what I mean. Moving on to question number 2. So it says on the labeled axes below, draw a potential energy diagram for this reaction. So potential energy diagram either looks like this or it looks like this. We have to determine if this is exothermic or endothermic first, and then determine which one we're going to actually put here. Looking at the chemical equation that's given here, it says N2 plus O2 plus the number here with the kilojoules. Again, this kilojoule means that it's the energy. So this 182.6 kilojoules is the energy that was added, okay, absorbed into the system in order for you to produce nitrogen monoxide. So again, if the energy was absorbed into the system, that's considered as endothermic reaction. An endothermic reaction is going to have the positive delta H because you added or absorbed the energy into the system. So in this case, the product is going to be higher than the reactant. Okay, so we're going to just draw that one in here. Now try number 1 on your own. And lastly, try on your own number 2.